All right, Unit 4. We are going to do the same thing that we did in Unit 3 with 3 different types of functions. An exponential function, e to the x, function a to the x, the log function, and then they are inverses of each other. We're going to talk about just inverse derivatives in general. Then we got linear approximations, and that will actually cover it for regular functions and their derivatives and the analysis of their derivatives. And we will have one more unit of derivatives, but of different types of equations, and we'll be doing some calculus word problems. That's Unit 5, and then Unit 6, we will switch gears and start tackling the next big problem in calculus. So this is more just what we've already done, only with e to the x and log x. So let's start with e to the x, and that's what we're going to start with, e to the x and a to the x. What is e is the first question. Everybody knows that you could type it into your calculator, and you get like 2.717. Let's see, e can be found over the division symbol, or you got e to the x. Doesn't matter, you get 2.71828. But we're like, where does that number come from? Well, e is a very important number. It's called the natural constant. It occurs naturally in a lot of mathematics. It's similar to pi, where pi just like pops up. This number 3.1415926.535. Pi is just equal to the circumference of a circle divided by its diameter. Like whenever you take any circle, take its perimeter, divide by its diameter, you will get pi. E occurs naturally with a lot of things that deal with infinities. And we will find that if you look at this expression, the limit as x approaches infinity, 1 plus 1 over x to the x, that you'll get e. Just to kind of show an example, I'm just going to plug in a big number for x, and I'll show you how I'm going to get a number very close to what my calculator says is e. So let's do 1 plus 1 over, I'm going to do 1, 2, 3, 4, 5, 6, 7, 8, 9. That's a big number. I'll take it to the x, 1, 2, 3, 4, 5, 6, 7, 8, 9. And I get a number that's very, very close to this number. The larger the value I'd plug in there, the closer we get to what e is. Okay, so it occurs naturally with infinities. It pops up in mathematics very often. Continuous compounding in finance. If you ever take a finance course, you'll talk about that. P equals e to the RT might be something familiar to you. But we're not going to worry about that so much as the derivatives. And before we talk about the derivatives, we need to talk about its relationship with the log function. Okay, if we talk about the function, and e is usually in functions where it's e to the power x. Exponential growth function, e to the x looks like this, whereas x approaches infinity, e to the x approaches infinity. It's exponentially fast growing. But as x approaches negative infinity, we talked about this in Unit 1, e to the negative x would be approaching, or e to the negative infinity would be approaching 0. Okay, there's e to the x. Now the log function is a function that mathematicians created to undo these exponential functions. The log function looks like this. We'll talk more about inverses and why like these are inverses to each other, and why this function looks like this, whereas this function looks like this. But this would be the log function, just a general graph. You could graph it using your calculator. But what's really important is that like e to the log x, if I replace x with log x, is just x, or the log of e to the x is just x. So they undo each other. So there would be situations, in this lesson and in this unit when you're asked to like find what is f of log 4 if f of x equals e to the x. Well, just know that e to the log 4, e to the log undoes each other and just gives us 4. Or if you have f of x equals log x, and we'll talk about this more tomorrow. If I ask you what is f of e squared, you'd say, okay, log of e squared, that's just 2. So e and logs undo each other, very important to know. But let's move on. Another thing that's very important about e that we'll use often is that e to the x is always positive. Doesn't matter if it's e to the x or like e to the negative x. This would be the graph of e to the negative x, just like the reflection of e to the x. It's always positive. It's important. Okay, but let's look at the tangent slopes of e to the x. Now I'm going to introduce some things with your calculator right now, how you can actually find derivatives with your calculator. For example, like x cubed, we know its tangent slope generator is 3x squared. And if I ask you what is the tangent slope to x cubed at 1, you know that you can get 3. Your calculator can also get 3. 2 different ways. And let's just make sure we understand that if I plugged in 2, f prime of 2 is 12. Okay. Here are the 2 different ways your calculator can get tangent slopes. First way is in your home screen. Okay. If you go to this math button, and hopefully you're watching this on YouTube and you can rewind if you're losing track of this, pop down to this n derive. Now, if you have a newer operating system, this pops up, which is nice. And look, this is like derivative notation. What we are going to tell our calculator to do is to take the derivative of x cubed and then plug in 1. Now, the calculator says that's 3. Oh, wait, no, it doesn't. It tells us that it's 3.00001. That's very interesting. Why? When we know the slope is 3 exactly, why is my calculator telling me that it's 3.00001? Okay, well, the important thing to know is that your calculator doesn't really know rules well. It doesn't know concepts well, but what it does have in its power is very strong computational ability. Your calculator would probably be doing the following. They'd probably be plugging in something like 1.001 and cubing it, and subtracting 0.999 and cubing it, and dividing that by this. So they're probably using the slope formula. And we remember that when we use this slope formula, we would get an approximation. So when we get this number 3.001, understand that this is our calculator's approximation. And we should know that if we would actually find the exact rate of change, it would exactly be 3. So your calculator uses the slope formula, not derivative rules like we use. So let's look at just the same thing. Math, go down to n derive. Now, if you have an older operating system, let's make sure we're comfortable with this. An older operating system, when you go to Math 8, you get n derive. It pops up like n derive. So if it pops up like that, this is what you would type in. It's a little bit more labor intensive in terms of typing, but it's not that bad. And let's do this for 2. You should get 12. And derive. You would type in the function, comma, with respect to x at the value. Okay, so where are commas? How do we do this? Well, we type in x cubed like this. It doesn't pop up to an exponent if you have an older operating system. Here's a comma right here. This is like a function, something that your calculator needs specific parameters to be able to execute. So it's take the derivative of the function with respect to x at x equals 2. And we should get 12. But look, my calculator is doing an approximation, and it doesn't get 12 because it is using a slope formula, 2 points close to 2. We should probably assume that the slope is just 12 because we know it is 12 using derivative rules. Okay? Now the other way we could find tangent slopes is using your y equals and graphing the function. Now, if you have graphed the function, you can go into second calculate. And down here at number 6, we see dy dx. Now I click dy dx and nothing happens. We can go ahead and plug any value in, just like we did with trace, and it gives us our dy dx. So we see 3.001. Again, your calculator is just approximating using a slope formula, so it's not exactly 3, though it should be exactly 3. Second calc, dy dx at 2, I should get 12. There's my dy dx at 2, I get 12. Okay, so make sure we understand both ways to find tangent slope generators. But now, let's use this graphical approach to find the tangent slopes to e to the x. Okay. All right. So the derivative of e to the x at x equals 0, 1, 2, 3, 4. Let's see. So dy dx at, let's say 0. Okay, so I am at this point 0, 1. At the point 0, 1, enter. My dy dx is 1. Okay, so at x equals 0, I had a slope of 1. Okay, that's neat. Maybe at 1, I'll have a slope of 2 or something. Let's see. All right, second calc, dy dx. We're going to go to 2. Okay, so at the point 2, which would be 7.389, that's e squared, I have a slope of 7.389. Oh, that's interesting. So the slope, sorry, I should have done, the slope of 2 is e squared. Let's go back to e. When x is 1, I have e. Let's see, second calc dy dx at 1. So at the point 1e, my slope is e. Okay, this is starting to be interesting / funny / intriguing. Let's do one more. If x is 3, I'm at the point 3 comma e cubed. My slope is e cubed. Oh. So e to the x is a fascinating function. It's the only function that this occurs. The tangent slopes of e are the same as the y coordinates of e to the x. Which means the tangent slope generator of e to the x is itself. That's crazy. If I ask you, like, what is, I'm going to write this in here. What is the equation of the tangent to e to the x at x equals 2? Well, my point would be 2 comma e squared. That's from my function. My slope, f prime, is just e to the x. F prime of 2 is just e squared. My equation would be y minus my y1 equals my slope times x minus x1. My y coordinate and my tangent slope are the same. Okay? Fascinating. If I have a to the x, it's a little bit more different. So a to the x is something like 3 to the x or a different number to the x. And I'm not going to get into why it is. If we start looking at implicit derivatives or log derivatives, you'd be able to kind of figure it out. But instead, I'm just going to tell you that the derivative of a other number to the x is the number to the x times the natural log of the number. So the derivative of 3 to the x is 3 to the x, natural log 3. You can kind of do that same process with e to the x. You can have e to the x log e, but we'll talk about how the log of e is like the log of e to the first, which is 1. So this is just 1, which is why we ignore this. Okay? But these are our new derivative rules. We're going to have to commit these to memory, that the derivative of e to the x is e to the x. This is the tangent slope generator. It's itself. And the derivative of a number to the x is a number to the x log a number. So this is going into our derivative rules arsenal. What we will find is that with a lot of tangent slope generators for e, we'll have e to a power where the power is not just x. So this is like e to the x squared, e to the negative 3x, 2 to the x squared. And my friend, the chain rule needs to be applied. We've probably forgotten about the chain rule. We did not have to use it often last unit, so it's back. Now we got to talk about outsides and insides. Well, in this case, if I have e to the power, we would consider that to be the outside, whereas the inside would be the power. And watch what happens when you take the derivatives of the outside and the inside and multiply those together. My y prime would be e to the power times the derivative of the power. What goes in there, what started out in the inside, is x squared. So e to the x squared times 2x. E to the negative 3x. Outside, inside. E to the power now can be an outside. The inside is the power. E to the power, negative 3, f prime, the tangent slope generator, e to the negative 3x times negative 3. So if you're asked to find like what is the tangent slope or the instantaneous rate of change of e to the negative 3x at x equals 2, just plug in 2. F prime of 2 is e to the negative 6 times negative 3. You could rewrite this as negative 3 over e to the 6th. That'd be the tangent slope. If I'm trying to find, y prime at 2 here, y prime at 2 would be e to the 4th times 4. So 4e to the 4th. Okay, those would be the tangent slopes. Now, if we have a number to a power, again, it is a chain because the power is not just x. The outside would be 2 to the power. The inside would be the x squared. The derivative of 2 to the power is 2 to the power log 2. So there's just something we'll have to remember is that like e to the x, its derivative is itself. Any number to the x, its derivative is itself times the natural log of the number. And then I got 2x, so my derivative y prime would be 2 to the power log 2 times 2x. It'd be 2 to the x squared log 2 times 2x. And I can plug in values for this to get tangent slopes to this. Something even more intense. Now I have 5 to the power. The inside would be this long power. The reason why I show you this is to remember to multiply with the chain rule. A lot of us like to add, but the chain rule is multiply by the derivatives of the composed functions. So multiply these together, which means you need to have the 6x plus 2 in parentheses. And then this power is the 3x squared plus 2x minus 5. Let's write it in like that. Three to the e to the x. Okay? This is interesting. Like the outside is the 3 to the power. The inside is e to the x. I could write the inside as e to the power and the, like a middle e to the power and the inside being x, but it works out since the derivative of e to the x is just itself that I don't have to worry about it. So I have 3 to the e to the x times the natural log of 3, times e to the x. This is a very common one we'll see. Its derivative, if you have e to the power times the inside, the power, e to the power times -1. Okay, so we would write this as negative e to the negative x. Really quickly, before we get into the next types of problems, like if I ask you to write an equation of the tangent to y equals 3e to the x at x equals, 3 to the e to the x, at x equals log 2. Let's go ahead and do that. Let's focus on this. Let's write the equation of the tangent to this at log 2. Well, we know we have y minus y1 equals m times x minus x1. Slope is my dy dx. That'd be y prime at log 2. The x1 is log 2. The y1 is y of log 2. Okay. Y of log 2. We will be expected to know how to do this. This would be 3e to the log 2. E to the log 2, like I said, e and logs undo each other, is just 2. So this is just 3 squared, which is 9. Y prime at log 2 would be 3e to the log 2, log 3, times e to the log 2. This is 9, because we just talked about e to the log 2 is just 2. This is log 3. This is 2. E to the log 2 is just 2. So I got 9 times log 2 times 2. I have 18 log 2. We don't know what the log of 2 is, so I just leave it. Y minus 9 equals 18 log 2 x minus log 2. We need to be comfortable doing that, writing these equations of tangent lines for these functions, plugging in values. But what else we need to do, and this is more kind of unit 2 stuff like derivative rules, equations of tangent lines. What we'll be doing mostly is unit 3 stuff. Is this function going up or going down at x equals 1? Remember, f of x is increasing if f prime is positive. F of x is decreasing if f prime is negative. We will need to find the sign of the derivative. So let's find the derivative. Now, the reason why I put these in is because we no longer have just chains, we have products. And we need to use the product rule. Now, the derivative of e to the 3x, I'll need to use the chain rule. E to the 3x has an outside and the inside. The outside is the e to the power, the inside is 3x. So I have e to the power times 3. So the derivative of e to the 3x is e to the 3x times 3. That's the derivative of the first. Times the second. Remember the product rule. Plus the derivative of the second times the first. I need to figure out if this is positive or negative. Well, if I plugged in 1, I might be able to compare the two things. But we will find that in the future, with all of our derivatives with e to a power, we notice that we could factor this very easily by pulling out the e to the 3x. And what's left is this 3 times x squared minus 2 plus 2x. And we could actually go even further if we wanted to. I got 3x squared plus 2x minus 6. I could plug 1 in. And I could have plugged 1 in here. Let's just look. So if I plug in 1 here, f prime of 1, I get e to the third, which is positive. E to any power is positive. And then 3 plus 2 minus 6, that's a negative. So f prime of 1 is negative e to the third. I don't really care about the sign. I know f prime of 1 is negative. That means f is decreasing. If I went back here and plugged in 1, I would have had negative 1 e times 3 e to the 3x, e to the third, because I'm plugging in 1, plus 2 e to the third. Negative 3 e to the thirds plus 2 e to the thirds is negative. So either way, you could have plugged in 1 at any point to find that the derivative of e to the 3x times x squared minus 2 is negative, which means my function's going down. We can see that if we graphed it. At 1, my function is going down. If I maybe zoomed, change my window, go down to negative 30, you can see at 1, it's close to being at a minimum, but it's going down. Okay? Let's look at e to the negative x over x plus 2. Reason why I put this one in is because you need to understand and remember the quotient rule. So, quotient rule, derivative of the top times the bottom, minus the derivative of the bottom times the top, all over the bottom squared. We got e to the power, and we have the power. Derivative of e to the power is e to the power, derivative of the negative x is the negative 1. So, for the derivative of the top, I would have had e to the negative x times negative 1 times the bottom, minus, in the quotient rule, the derivative of the bottom times the top, all over the bottom squared. To evaluate this at 1, let's see. I'm going to plug in 1 now. I could simplify by pulling out an e to the negative x, but I'd have e to the negative first times negative 1 minus 1e to the negative first over 3 squared. This is negative 2e to the negative first over 9. Or negative 2 over 9e. We need to be prepared to get that value, first of all. We could have factored out the e to the negative x. E to the negative first is a positive. This is very important to know that this is a positive number, so if you did factor it out. But we see y prime of 1, which is that is negative, so I know that this function is decreasing as well. Okay, another one just like that. Is sine x e to the negative x increasing or decreasing at x equals 0? Let's find out. Again, we have a product. We have a product rule coming up, and within the product rule, we will have a chain. So in the product rule, I have the derivative of first times the second, plus the derivative of e to the negative x. We talked about it before. It's e to the x times negative 1. It's like the derivative of the outside times the derivative of the inside times sine x. Plug in 0. I get f prime of 0 is cos 0 e to the 0 plus e to the 0 times negative 1 times sine 0. Cos 0 is 1. E to the 0s are just 1. I'll have 1 plus 0, which is 1. So that's positive. F is increasing. It would be important also to understand that we could have factored this and pulled out the e to the negative x and had cos x minus sine x left over, e to the anything is positive. Cos of 0 minus sine 0, positive. Since the derivative is 0, f is increasing. Okay? And now we get into more things that we did last unit, only with e to the x. So like critical points, locations of relative extrema, extrema, concavity. When are we having derivatives that are negative and increasing? So we'll look at the first and the second derivative. When is f increasing and concave down? All of this stuff we will need to be able to do from last unit with ease. And we'll find some commonalities with them. They're not that tough. First, we need to be prepared to use the product rule. Product rule occurs often with the setups of these problems. So this is a product. Make sure we use the product rule. Derivative of the first times the second plus the derivative of the second times the first. Now, critical points are when our derivative is 0 or undefined. So I need to take this derivative and set it equal to 0 or see when it's undefined. How do I solve that? You know, I got 2x e to the x plus e to the x, x squared minus 3. We will find that what is going to be easiest for all of these is to factor out the e to the power. And after I do that, I have this simplified form. Now, right away, this part is never 0. It's always positive. It'll approach 0 if I plug in negative infinity. But if you plug in any like whole value, any value at all, it's never going to be 0. So I actually just need to worry about this part in here. I know this is x squared plus 2x minus 3. I could factor this to be x plus 3, x minus 1. That is going to be at negative 3 and a 1. I'll have critical points. Again, nothing from here, nothing here. Now, what we would be asked to do then, find the x locations and type of relative extrema, same function, is analyze the signs of my derivative around these critical points. This is when f prime was 0. We have our simplified f prime right here. We need to understand no matter what value I plug in my interval, like 2, like 0, like negative 4, e to the x is positive. If I plug in 2, I get a positive and a positive, 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 positive. If I plug in 0, e to the 0, still positive. It's 1. So I got positive, x plus 3, positive, 0 minus 1, negative. E to the negative fourth is 1 over e to the fourth. It's a fraction. It's small, but it's still positive. So positive, negative 4 plus 3 is a negative. Negative 4 minus 1 is a negative. So this is a positive. So since f prime is positive, that's telling me f is going up. Then f is going down, then f is going up by looking at the signs of its derivative. So f is increasing, then decreasing, then increasing. X equals negative 3 must be the location of a max. X equals 1 is the location of a min. To confirm our analysis, even though we have no idea what the function x squared minus 3 times e to the x looks like, I know because of my work, I'm going to have a max at negative 3, a min at 1. If we zoom standard, I think it'll fit. Now, it doesn't look like it, but if I zoom in around negative 3, let's trace over to negative 3. And zoom in there. We could see we increase to get a max, and then we start going down after negative 3. Start going down, start going down. So that's really great. Back to zoom standard, we see I have a min at x equals 1. Okay? So we did that analysis, even though, man, this function, oof, I have no idea what it looks like. Well, we just kind of have a general idea of what it looks like. All right, when does x squared e to the x have relative extrema? When is f decreasing? All right, well, define extrema, figure out when f is going up or down, To figure out when f is going up or down, look at the signs or do a sign analysis of f prime. When is f decreasing? Something is decreasing. F is going down when f prime is negative. All right, so I need f prime. I need to figure out the signs of f prime. Once again, product rule. Derivative of the first times the second plus the derivative of the second times the first. Set this equal to 0 to see when my signs could change, see when it's undefined. I don't have to worry about the undefined. There's no denominator. Factor out the e to the x. We can then factor this inside. And I get something like that. So 0 and negative 2 are interesting points. Reminding ourselves that e to the x is always positive. If I plug in 1, positive, 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 negative 1, positive, negative, positive, negative 3, positive, negative, negative. So f is decreasing when f prime is negative. That occurs from negative 2 to 0. F is going up, then down, then up. X equals negative 2 has got to be the location of a max. X equals 0, it's got to be the location of a min. All right? All through sign analysis of derivatives. Let's look at x over e to the x, okay? Quotient rule. Derivative of the top times the bottom minus the derivative of the bottom. The derivative of e to the x is e to the x times the top all over the bottom squared. E to the x squared. Well, I got to set this equal to 0 or see when it's undefined. Now, a lot of you are probably worrying, oh, I have a denominator. I need to see when it's undefined. E to the x squared can never equal 0. E to the x is always positive. We'll talk about how you could solve this in the future. One thing is important, that if you have a power to a power, we could write this as e to the 2x. But again, e to the 2x, e to any power is just positive. You can take the natural log of both sides, but we will find that there is no natural log of 0. So this cannot be done. So we actually don't have to worry about the undefined part as well here, as long as we understand that the bottom is going to be positive. We do need to worry about the top equal to 0. If I factor out e to the x, I have 1 minus x equal to 0 over e to the 2x. That's my simplified f prime. This could equal 0 at 1. If I plug in 2, positive, 1 minus 2 is a negative. E squared, positive, I have a negative. If I plug in 0, e to the 0, positive, 1 minus 0, positive, e to the 0, positive, positive. So f is going up and down. So x equals 1 is a max. I've never looked at x over e to the x. Let's look at x over e to the x. X over e to the x. At 1, we have a max. It's a, I don't know, like a huge max, but at 1 we obtain a maximum value, and we will start decreasing after 1. We will be approaching 0. We know that we're approaching 0, and this will be going into, if we had to do a curve sketch of this, I would probably look at the limit as x approaches infinity of x over e to the x. I know that would approach 0. So I can kind of tell that all the way over to the right, I'm approaching 0. I have some sort of max. Would it be at 1 over e? So 1 over e would be my max. And we could look at, if we're approaching negative infinity, we'd be approaching a negative value like that, and we would get that. Okay, great. Concavity. What is a function's concave down? You look at the second derivative. And if the second derivative is negative, we're concave down. You already are given the first derivative. Okay, so to look at the second derivative, just take the derivative of your first derivative. It's a product, use the product rule, derivative of the first times the second, plus the derivative of the second times the first. Set that equal to 0, see where the signs could possibly change. I'll pull out the e to the x. I have 2x plus 1. This is 2x plus 3. So the 0 will be at negative 3/2. If I plug in 0, I get a positive. If I plug in negative 2, I would get a negative because e to the x is always positive. This could change signs. This is f double prime, which is telling me f is concave down and then concave up. F is concave down from negative infinity to negative 3/2, or x is less than negative 3/2. Okay, so we see these are very similar in all of our approaches. We end up just factoring out an e to the x. All right, let's go a step further. We want to find when f has an f prime that is negative and increasing. Okay, so f prime that is negative, that's fine. I could do a sign analysis of f prime. F prime that is increasing, that is when its derivative is positive. Okay, so f prime negative, f prime increasing, f double prime is positive. I need to do a sign analysis of both f prime and f double prime back to the end of unit 3. I have a product, use the product rule. I factor out e to the x, set it equal to 0. My first interesting location on the graph of f prime would be negative 1. Let's go and find the second derivative. Now, it does not matter when you find the second derivative. You could go back up to here and just understand you'd have the derivative of e to the x, which is e to the x, the derivative of e to the x times x, which you could use the product rule, or you could take the derivative of this using the product rule. Doesn't matter. I'll take the derivative of this. It's the derivative of e to the x, that's the first times the second, plus the derivative of the second times the first. That was this derivative. If I did this derivative, I'd get, just ignoring the 1, the derivative of e to the x is e to the x plus, then product rule, derivative of the first times the second plus the derivative of the second times the first. So I'd have e to the x, e to the x, e to the x in 3 locations. We end up getting the same thing. All right, so regardless of which way you do it, this is the second derivative. We can then factor out an e to the x. I'll get 1 plus x plus 1, or 2 plus x. So for f double prime, an interesting sign will be negative 2. Make sure it's in order. Let's do the analysis of f prime. To do the analysis of f prime, I'll look at the simplified form of f prime. Plugging in 0, I got positives. Plugging in negative 2, I'd get negatives. For f double prime is this simplified form. We would have positives and negatives. Plugging in values like 0, plugging in values like negative 3. Remember, e to the x, always positive. Okay, so reminder from last unit, this is telling me f is going down, then going up. This is telling me that f is concave down, then concave up. I don't really care about that because it's asking when f prime is negative and f double prime is positive. F prime is negative, f double prime is positive. Here, from negative 2 to negative 1. We know that when f prime is negative, I'm decreasing. F double prime is positive, concave up. So f is decreasing, concave up, only from negative 2 to negative 1. Let's look. X, e to the x, from negative 2 to negative 1. From negative 2 to negative 1, decreasing, concave up, negative 2 to negative 1. I'm decreasing, concave up. I'm decreasing concave down all the way to negative 2. I have a point of inflection, and right here from -2 to -1, I'm concave up and decreasing. It's really cool. Decreasing concave down, decreasing concave down, decreasing concave up, and then I'm increasing concave up the rest of the way, increasing concave up the rest of the way, which is what I see, which is really cool that we can do this, all from signs of derivatives. All right, e to the negative x squared. What is f increasing and concave down? So I got to figure out when f prime is positive. I got to figure out when f double prime is positive. Sorry, negative. Okay, well, for f prime, let's make sure we understand that we have a chain, a composition. I need to use the chain rule. So f prime would be e to the negative x squared times negative 2x. Set that equal to 0, or see when it's undefined. Don't worry about the negative x squared. E to any power is just going to be a positive. We just need to worry about this negative 2x. 0 would be an interesting location. Now in this situation, to the right of 0, e to the negative first, positive, but I had negative 2 times 1, negative. Plug in negative 1, negative 2 times negative 1, positive 2. Okay, now let's look at the second derivative. This is tricky. I have to use the product rule now. The derivative of the first is that times the second plus the derivative of the second times the first. Notice how different that is. I had a chain, now I have a product. Most of us screw up on that. When I have to not do the same rule twice, I have to do one rule the first time and then do a different rule the second time, which includes the chain rule from the first time. So once again, this is the derivative of the first, this is the second, this is the derivative of the second times the first. To find when this is 0 or when this is undefined, pull out the e to the negative x squared. I have negative 2x times negative 2x, which is positive 4x squared, plus negative 2. I will set that equal to 0. I need to solve this. I can go ahead, if I wanted to, and just set up an equation, 4x squared plus negative 2 equals 0. Add 2 divided by 4, x squared is equal to a half, x is equal to plus or minus root 1/2. So, for f double prime, I need positive root 1/2, and I need negative root 1/2. If I plugged in something like 1, this, remember, always positive. E to any power will always be positive so long as it doesn't have like a negative coefficient in front of it. It's like negative 2 e to the negative x squared. That'd be a negative, but e to the power is always positive. So, plugging in 1, positive, 4 times 1 minus 2, positive. Plugging in 0, positive, this would be 0 minus 2, negative. Plugging in negative 2, positive, a lot positive. So f is going up and down. F is concave up, concave down, concave up. When it's f increasing and concave down, increasing concave down is going to be from negative root 1/2 to 0. When is f increasing and concave up given f prime? All right, so make sure we understand what we're given. We are given f prime to find out when f is increasing, find out when f prime is positive. How do you figure out when this is positive? Set it equal to 0. See when it's undefined. I get plus or minus root 3. These are important parts of f prime. We need our second derivative. Product rule. derivative of the first times the second plus derivative of the second times the first. Factor out the e to the x. Rewrite this so that I can see that it can factor. Interesting points are at 1 and -3. Now, make sure you put these in the right order. 1 is less than root 3. Root 3 is like 1 point something. -3 is definitely bigger than negative root 3. This is f double prime. So, this f prime, signs of f prime, we just have to really look at the x squared minus 3. Positives, negatives, positives. F double prime, F double prime, F double prime. We did this earlier. Positives, negatives, positives as well. When is f increasing? F is increasing when f prime is positive. When is f concave up? Concave up when f prime is positive. So I have two intervals. Oops. Should write concave up, not an arrow that's up. I'd be from -infinity to -3. Stop there because I'm concave down from -3 to negative root 3, and then from root 3 to infinity. Okay. All right. Last couple types of problems are table problems. So understanding your derivative rules, finding derivatives of this, given some information. So I'm trying to find f prime of 0. Let's find f prime of x. So remembering, with table problems, don't forget your derivative rules. Derivative of the first times the second plus the derivative of the second. Now, remember, e to the negative x, outside, inside, e to the power, negative x. The derivative of e to the negative x would be e to the negative x times -1. So, negative e to the negative x. That's the derivative of the second times the first. Trying to find f prime of 0. I got g prime of 0, which is 2. I'll have e to the -0, which is just e to the 0. E to the 0 times g of 0. G of 0 is 2. Sorry, g prime of 0 was 3. G of 0, 2. So this ends up being 3 plus -2, which is just 1. That is f prime of 0. X, e to the f of x. Why don't we just start with e to the f of x? If I asked you to take the derivative of e to the f of x, the outside would be e to the power, the inside would be the power. The derivative of e to the f of x would be e to the f of x times f prime of x. I can see how a lot of students would get that wrong. It's the derivative of the outside, which is just what we have started with, times the derivative of the inside. If I wanted to plug in 2, e to the f of 2 times f prime of 2, I get 3. Now, if it was, let's say, capital H of x, maybe let's not use that notation. Let's turn this into a m of x was x e to the f of x. Let's look at m prime. Product rule, derivative of the first times the second, plus derivative of the second, chain rule, times the first. Now, if I wanted to find m prime of 2, I'd have e to the f of 2 plus e to the f of 2 times f prime of 2 times 2. I'd have 1 plus 6, 7. Two more. Product rule. Derivative of the first times the second, plus derivative of the second times the first. F prime of 2. 2 squared, log 2, g of 2, g prime of 2, 2 squared. 12 log 2 minus 8. I'd leave it as that. Last one. Goodness. Product. Derivative of the first, 3x log 3 times the second, e to the f of x. Plus, derivative of the second, we talked about it, e to the f of x times f prime of x. Outside is e to the power, inside is the function. Derivatives e to the power, derivative f prime. Derivative of the second times the first, plugging in 2. 9 log 3 e to the 0 plus e to the 0, because f of 2 is 0. F prime of 2 is negative 1 times 9. So I got 9 log 3 minus 9. That's it.